have our model-based covariance matrix, the capital sigma, or you can call it expected covariance. That covariance is decided based on your model. So with different model, you will have different covariance matrix. Actually, there are two types of matrix which are really important in our SEM course. Okay, or in other advanced step course. One is a model-based covariance matrix, just we derived here. The other one is a sample-based covariance matrix. After we collect our data, we can immediately generate the sample-based covariance matrix. In that case, you don't need to know any model. That matrix is just based on your data. Okay, so we have two types of really important covariance matrix: sample-based and model-based. So we're trying to create a model-based covariance matrix, trying to kind of like explain the sample-based covariance matrix. Of course, I will explain this logic in estimation class, but I just want to show that this is one type of covariance matrix, and later on we will see another type of covariance matrix, and we're trying to get the difference of them, or to try to match if these two are really well fitting or not. So what we are doing here is trying to get the capital sigma, which is a model-based covariance matrix. It has to based on our model. Okay, so we use algebra calculating to calculate each element. Okay, we use the algebra rules to calculate each element in our capital sigma. That's one way. And we use simple regression example. We also have a multiple regression example. And in the homework one, we use a mediation model. That is called a mediation model. We will talk about that model after we explain all of this logic foundation part. And now we are going to look at the other two methods. One is called the tracing method. The other one is called the matrix representation. Okay, basically we're gonna use RAM matrix to do some calculation. So, okay, so we have two more methods, but what we are going to do here is trying to get the covariance matrix, the capital sigma. Okay, that's our goal. And we have simple linear regression example. So we have X, which is an independent variable, Y is a dependent variable, and X gonna cause Y. Y is the outcome, and the coefficient is beta. That's simple linear regression. And suppose we know the variance of X is sigma X squared. By looking at the model, we manually derived the capital sigma here. Okay, we have this covariance between X and Y. We have this is the variance of Y. So this is our first example. So you're gonna you don't need to memorize this form, but maybe you will meet this matrix again, because we are going to use second method and the third method to get this matrix again. Okay, this is the same answer, but we use different methods. Okay, and then we have a multiple regression example. By following the same rules, okay, we just replace Y by using the multiple regression expression, and then do the expansion, and then follow some rules, and we calculate each element in that capital sigma. And in this case, we assume that X, W, Z are three independent variables, and Y is a dependent variable. So these three influence the outcome Y together. It's multiple regression. And we assume this part is known because this part is coming from the independent variable part. We know the variance of X, variance of W, variance of Z, covariance among these three variables. Suppose this part is known, and we manually derived this element, which is a covariance between X and Y, one independent variable and the dependent variable Y. And similarly, we derived the element of covariance between W and Y, covariance between Z and Y, and the variance of Y. Okay, variance of Y. And again, you're gonna look at this matrix again, because we will see the matrix again by using the second method and the third method. Okay. Okay, so that's a review. Yeah, as I mentioned, today we're gonna go through this the other different methods. Okay. And I also uploaded the reference to ELC. This part mainly based on the Lorraine's SEM textbook. I have already scanned the chapter, and I think I only put 4 pages or 3 pages. That's the focus of this part. And for this part, I also uploaded a paper talking about this method to ELC. So if you have any question or if you want to read further about these 2 methods, you can just read those documents. And also the chapter, one chapter from the Boland's book. Okay, so for the SEM Boland's book. Okay, so now let's look at the tracing method. Tracing method, we do not need to know the model, the mathematical form of the model. Instead, we needed to clearly know the path diagram. Okay, as I mentioned, okay, we have 2 ways to show the SEM model. One way is to use the path diagram, the other way is to use a mathematical form, okay, the models. So by using this way, the path diagram is the key point. Okay, you don't need to know the equation. And we follow some rules. Again, we have a lot of rules, and the general rules that no loop. Okay, I will show you the detailed rules, but generally you cannot just use a loop. You cannot go to one variable and then go back again. So that's not allowed. And no going forward then backward. Okay, just like loop, you cannot do this. Okay, it's one of the general rules. And a maximum of 1 double-headed arrow. You will see that by following some rules, you will have some single-headed arrow path or double-headed arrow path. But one rule is that there's a maximum 1 double-headed arrow. You cannot have 2 or 3 or 4 double-headed arrow path. Yeah.
So when you mean double-headed arrows, you mean
covariance or correlation.
Right. So
yeah,
instead of like on the homework where the X and Y, it'd be going backwards from Y to X, correct?
It's double-headed arrow. Yeah,
okay.
Not a 2 single-headed arrow. Yeah.
Correct.
Okay. Yeah, I will show you the details. Okay, so generally, I summarize all these rules here. It looks, yeah, there are a lot. So we have rule 1, 2, 3, 4, 5, 6, 7, and inside rule 2, we have 2.1, 2.2, 2.3, 2.4, 2.5. Okay, now let's look at each of them one by one. Okay, let's just look at the first rule. That's for covariance. When the question asks you about the covariance between 2 variables, you can apply this kind of rule. Okay, if there's a double-headed arrow between 2 variables, then that's it. That's a covariance between that 2 variables. Suppose you have x and y, 2 variables. If I ask you what's a covariance between x and y, and these 2 are connected by a double-headed arrow, then this value is a covariance. Okay, a very simple case. Okay, so the covariance between x, y is the value on the double-headed arrow. Okay. And rule 2. Now let's look at the single-headed arrows. If the covariance is through single-headed arrows, then you have a lot of like sub-rules, different cases. Okay, for example, in this case, okay, 2.1, you're gonna start backward from the dependent variable, because if you have single-headed arrow, you have independent variable, you have dependent variable. Dependent variable, that means the variable of this end. Okay, so you're gonna start backward from the dependent variable to the independent variable, go back to the independent variable. Use a path coefficient. So for single-headed arrow, there's a coefficient. Okay, you're gonna remember that coefficient. Use a path coefficient to multiply the variance of the independent variable. Look at this case. You have single-headed arrow connect these two variables from x to y. And the question is that what is the covariance between x and y? Between them, there's a no double-headed arrow. Instead, there's a single-headed arrow. Then the first step, start from the dependent variable. Start from the dependent variable. Goes back to the independent variable. Reverse the direction of the single-headed arrow. Stop here. That's not the end of the story. You have to times the variance of the x. This is one double-headed arrow. You have used the one double-headed arrow, then that's it. Maximum one double-headed arrow. Beta times the variance of x, stop. So the covariance between x and y is the beta times covariance of x. That's it. Okay, so in this case, you use the one time of single-headed arrow, you use the one time of double-headed arrow. In the previous case, you just use the one double-headed arrow. Okay, that's it. The maximum number of double-headed arrows is one. Okay, so in this case, you're gonna start from y, goes back to x, and times the variance of x. And that value is a covariance between x and y. Got it? Good. Okay, quite simple. Okay. Yeah, that's rule 2.1. So far, so good. Okay. Now, under rule two, we also have 2.2. Okay, if there's a double-headed arrow covariance connected to independent variables. Okay, so in this case, we have x here, z here, and we have double-headed arrow connected to these two parts. And in this case, another component that can be formed by going through the double-headed arrow to the adjacent variable. So actually here, there are two components. So if you have three variables here, okay, you have x here, you have y here, you have z here. But the question, suppose I ask you, what is the covariance between x and y? X and y. So z is not included in this question. But if you actually look at the path, let's look at this case. Okay, so one case is that starting y, the dependent variable, go back to x times the variance of x. That's it. This is one part of the variance between x and y. But now the situation becomes a little bit more complicated because you have another variable. Okay, there's a double-headed arrow covariance connected to independent variable. Okay, another component can be formed by going. You can also consider this path. This path is also a component of the covariance between x and y. So starting from the y, the dependent variable, go back to the single-headed arrow. This is another single-headed arrow. Go back to z. Z, there's a double-headed arrow between x and z. So you go through this double-headed arrow, stop at x. Okay, so finally you have two components. This is one part, and this is another part. For each component here, you use a double-headed arrow once. For this component, just use this double-headed. For this component, you just use this double-headed arrow. You cannot do this, okay? Look at me. You cannot start from y, go to z, double-headed, and then goes to x. No, that's not allowed. It's the general rules has been violated because you have two double-headed arrow in that case. Okay, and then you cannot just stop here. Okay, if you want to use this double-headed arrow here and you stop here, you didn't reach X because finally you're gonna stop at X. You start from Y, you're gonna stop at X. So if you use this circle, not circle, okay, double-headed arrow and stop here, that's not the one component because you have to go back to X. Yeah, question?
So could we do it mathematically where we go Y to Z and then the covariance there for step one and then go Y, Z, and then the one going up to X as a plus to where we add a second component or no?
Yeah, this is second component. This is a, so that means covariance between the X, Y actually has two paths. Yeah,
Yes,
one
okay.
path is from here, the other path is from here to here.
Okay.
Yeah. Okay, now let's look at another case. Look at this case. We have kind of like a twin here. Okay, we have a lot of like single-headed arrow. If the adjacent variable connected to the dependent variable through a single-headed arrow, keeping going forward, backward, keep going backward to the path, and then pass through the variance and then go back. Okay, so now again, the variable y is here, variable x here. Okay, now I ask you, what's the covariance between x and y? We have so many single-headed arrows here. So what should we do? Always think about that. Okay, start from the dependent variable, stopped at the independent variable, or not. Sometimes it's not independent or dependent. So anyway, so you're gonna start from one variable, in this case, start from y, and then stop at x, the other variable. Okay, so here, start from y, goes back to the direction of the single-headed arrow. Okay, and you're gonna write down the coefficient of the path, and then goes back to x. Okay, and this is another coefficient. You're gonna multiply this coefficient. But this, you cannot just stop here. This is not the end of story. You have to go back to W. And then there's a variance of W. And then W is not your endpoint. You have to go back to X. Okay. So you start from Y, go back to Z, because it's single-headed arrow. Okay, if you have single-headed arrow, just goes back, and then goes back to X. But this is not the end. Okay, so you have to go back to W, and then follow the double-headed arrow here. Variance of W, but you cannot stop. Just stop here. You have to go back to X. So for this path, actually you use it twice. This time and going back to x, so twice. Okay.
So why would you've got a written B W twice? Why wouldn't you just put a 2 in front of it?
Well, this is not 2 squared, sigma squared.
No. I'm saying the BW. If we're using it twice, why don't we just
squared?
Yeah.
Beta W squared.
Yeah.
But this order shows you the path.
Ah, okay.
Okay, you will have homework 2. For homework 2, you're gonna do the similar exercise. Please use the correct order. You cannot just use beta squared because I'm confused. Which one is the first? Okay, just show the correct order. Based on this order, beta z is the first step. Beta z is first step. Second step, beta x. Second step. Third step, beta w. Third step. And then this is double-headed arrow. Fourth step, okay, double arrow. And then fifth step. It clearly tells you the order. Yeah, question.
So, and like how we did in number 1, where we had to carry the covariance over to multiply out and then add, is that like the similar in fashion, if that makes sense? For example, we see the variance W squared beta W.
Yeah, variance of W, yeah.
So is it like we carry that covariance over when we multiply and add out?
Sometimes you're gonna use variance, sometimes you use a covariance. Yeah, you're right. In this case, we use a variance of W.
Okay.
Yeah, you carry the variance of W.
I hope that makes sense.
Okay.
Now, also, I hope that my question made sense.
Can you say your question again? So you're gonna.
So my question was in how we did number 1. Homework number 1, where we had to factor out each variance. So for example, covariance of x and y, so it'll be covariance, whatever the value of x is, whatever the y, the variance of y. So for example, if x equals AW plus V, we would do covariance.
W and V.
Yes.
That depends on my question. So sometimes I ask you the covariance component, sometimes I ask you the variance component.
Right.
This rule is for covariance.
Right.
And next we will have the variance rules. Yeah.
Right. Well, that was my question basically. Will be.
Yeah.
Okay.
Yeah. If you have AW times V and W and V, in that case, W and V are independent, assume. That in that case, the covariance between W and V is 0.
Okay.
Yeah. So again, you're gonna follow the correct order. So the order is very important. Any question for this rule? Clear? Okay. Yeah, actually this, okay, rule 2.4, actually this is one of our general rule. Okay, so one can only go through double-headed arrow once. Actually, this is one of very important general rule. So you cannot use variance and times covariance and times covariance. For example, if I ask you these two covariance between these two variables, you cannot use beta z times the variance of z times the covariance between these two times covariance between that's not allowed because you use 3 double-headed arrow in that case. Okay. Yeah, so again, so if you want to look at the covariance between x and y, then you can use this path or you can use this path and add these two components together. Okay, so it will be beta w times the covariance between w and x and plus beta z times the covariance between x and z. That's it. You cannot just go to here and go to w and go to z or go to x. No, that's not allowed. Or you're trying to go to w, go to z, go to x. No, that's not allowed. Okay. Okay. And the rule 2.5, a single-headed arrow in a flow should be multiplied. Actually, we applied this rule in the previous cases. If you have single-headed arrow, then you should times the covariance between them again, because this is another example. Just look at the covariance between x and y here. Covariance between x and y. So obviously, this is one component. Okay, this is a really easy component. Starting from y, go back to x, variance of x, stop here. But actually, we have another path. Okay, starting from y, go to w, go to z, and stop at x. Because here we have single-headed arrow, and you kind of like reverse the direction. So you have another component, beta w times beta z here, and stop x times the covariance between z and x. Okay, because here we have a single-headed arrow, and in this flow. Okay.
So you would ignore the variance for W.
Okay,
because that's
so
a double-headed
his question is that, yeah, his question is that I ignore the variance of W. Okay, if I consider that,
You have to stop.
yeah, so I follow this path and I use this W
You're done.
and I go back here. And how should I start from Z to X?
Correct.
This is the second double-headed arrow.
Right.
That's not allowed. Yeah.
Correct.
Yeah. So we have to
Right.
ignore this part. Yeah. Yeah. Good.
Okay, I was just making sure I was following this.
Yeah, you're right. You're correct. Yeah. Any question so far? Okay. Okay, that's rule 2. Okay, if we have single-headed arrow, connect these two variables. And rule 3, actually, we have already used these rules in the previous examples. Trace all paths towards a variable backward and add them together. Okay, so sometimes you have different paths. you have different patterns, you have different approach. Then add each component together. Rule 4, when encounter a double-headed arrow variance, going back again, we applied this rule in the previous examples. So if we have variance part, then you should use a variance part. Oh, no, this is not, okay, this is a double-headed arrow, okay. This is variance. Now it's not the covariance between x and y. Previously, we have the example between covariance between x and y. So beta times variance of x stop here. But now the question is that what is the variance of y? So we start from y, we should go back to y. The question is different. It's not a covariance between x and y. Okay. So we start from y and goes to x, and you have to write down the beta here, and then the variance of x, but you cannot just stop here because this is a variance of y. You have to stop at y. So it goes to this way again. Okay, follow this single-headed direction times beta again. So that's variance. That's for variance. Okay. Okay. So yeah, so it should be beta times the variance of x times beta. Again, the order is very important. You cannot just simplify it as beta squared times variance of x. I will not give you full credit. You have to show the path. Okay. And then another case, this is for variance. Okay, so for variance again. So we use the same path diagram. We use it before for covariance. Now let's look at the variance of y. Variance of y. So that means we have to start from y, go back to y. Okay. So we can use this part. Okay. We can start from y, goes to w, go to z, and go to the x, and then go back to y. So beta w here goes to z, the first step here, and the beta z, the second step, go to z, and then the covariance between these two variables, because here we have double-headed arrow. Once we use this double-headed arrow, you cannot apply this variance again. So, but you have to go back to one. Okay, so times beta x. Of course, this is just one component. Okay, this is one component of variance of y. Actually, there's another component starting from y, go to x, the variance of x, and go back to 1. This is just one component by using this path. Okay.
So that's an incomplete component.
It's just one component. Actually, if you really want to calculate the variance of y, there's another component. Beta x times the variance of x times beta x. Two components, add them together, we have the variance of y. Yeah.
I have a question.
Yeah.
So then we can't go back. So like,
Right.
we can't go back the other way, right?
That's
so
what I was going to ask.
okay. Like we couldn't go from y to x and then x to z and then z to w.
You're right. We have another path.
Yeah.
You're
There's
right.
another-
Yeah. We started from y, goes to x, and go to z, go to w, go to yeah.
So would there be 3 components then, or just 2?
Exactly. Okay, so that's good point, because in the next example, you will see that we have different paths, but if you change the order, the same path, but if you change the order, there will be 2 components. So you start from the same variable, the same path, but different order, then that will be different. Just like this, okay? So actually this is the same path, but we use different order, starting from here, or something. That would be different, yeah.
So would the 4th component be going from y to w, the variance of w, and back to y? Would that be the 4th component then? Going along the same logic of x?
So which one?
So go from y to w,
Yes,
the variance of w, no up,
variance of w.
and go back to y. Because you did that with
Oh,
x.
yes, you're right.
So that'd be the
Yeah.
4th component.
Yes,
Okay,
good.
I'm just making sure I'm
Yes,
following.
yeah. Okay, this is just one component.
Okay,
Yeah, but this component is calculated for the by using this rule. Rule
I
5.
just didn't
okay.
want to, something unsaid come up
Yeah.
on the homework.
When encounter double-headed arrow covariance, pass it and follow a single-headed arrow. Because by following this rule, you have to use the single-headed arrow here. But you have other components. We didn't use this path. Yeah, good. Thank you. Yeah. Rule 6. Again, this is for variance. Okay, one can pass double-headed arrow only once. This is true for variance, true for it's true for covariance. Okay. Yeah, so for any component, one can either pass the variance or covariance, but not together, not variance and the covariance together. No. And the rule 7, paths with different order are different. Okay. So if you show me different order, that will be different. Okay, different order or even with the same path, the same loop or same path, but the different order will be different. Yeah, that's rule 7. Okay, so I just explained each rule here. Okay, explain the details of these slides. Actually, these slides. Okay, and you're gonna apply those rules to the following example. Okay, we will start again. We will start from a simple linear regression. So far, so good. Any question? Okay, let's look at the example of simple linear regression. So we have dependent variable y here. We have independent variable x here. And of course, we have the residual e here. And we assume the mean is 0. In most cases, we assume the mean of the SEM model is 0. And of course, and later on, we will consider the mean part only. Okay, and we can combine mean part and covariance part together. But the focus is the covariance part or the variance part. So we assume the mean 0, and we have x goes to y, and we have e. Now, the question is that what is the covariance matrix between x and y? Again, here we have two observed variables, x and y, one independent variable, one dependent variable. What is the covariance matrix of this 2x1 vector? So this is a 2x1 vector. Covariance matrix. It's 2x2 matrix. 2x2 matrix. You have to figure out the 4 elements. And this part, suppose this is given. This part is given, variance of x. Then what is this question mark? What is this question mark? You don't need to figure out this part because this is magic. So it's these two elements are the same. But you needed to know what is the covariance between x and y, what is the variance of y. Now forget about this equation. By just looking at this path diagram only, forget about this part. Okay, just look at this path. Covariance between x and y. We can just apply the previous example, right? What is the covariance between x and y? Starting from y, go back to x times the variance of x. That's it. So this is beta times variance of sigma x squared. That's the correct answer. Actually, we did it before. We did using the first method. Remember, we just showed this matrix in the very beginning of this lecture. Then you needed to know, you needed to calculate the variance. This is the variance of y. Okay, this is y. This is y. Variance of y. So the question is that what is the variance of y in this case, in this path diagram? So by applying the previous rule, so starting from y, first, how many components? Variance of y. How many paths? Yes, actually there are 2 paths. Yeah.
Because you go to the left
Yes,
to X,
exactly.
and then you go to the right
One
to
component,
arrow
starting from y, go back to x.
and loop.
You have to write down the beta here. And then the variance of x, you have to go back to y.
Yeah.
Go back to y and the times beta again, twice, okay? Then that's one component.
Plus.
Yes, the other component of 1
Mhm.
times the variance of sigma, variance of E is the sigma squared, times 1 again, go back to Y again. So you have components. So this is one component. Okay, we start from Y, go to X, and actually you have this double-headed arrow goes back to Y. Okay, this is one path. So here you have beta, you have sigma X squared, you have beta. So if you write it down, actually it's a beta times sigma X squared times beta. This is one component. But you have another component. Okay, go back to E and the double-headed arrow here, stop here. Okay, so this is 1, and this is sigma E squared. This is 1. So this, the other component is 1 times sigma E squared times 1. This is a second component. And add these two together, add these two components together, you will have the variance of 1. So that's why we have this variance. Okay. So of course, the final answer is kind of like a simplified version. So we have beta here. So beta squared and variance of sigma squared, variance of X here, sigma squared, plus 1 times this one. This is a sigma E squared. That's our variance of Y. So by using this method, I didn't use the equation. I didn't think about this beta times X plus E. I just look at the path diagram. Yeah, and I figure out the capital here, the form matrix here. Okay. Clear? Good. That's really simple. Now, for multiple regression, it's not so easy. Okay. Yeah, because we have so many paths, we have so many components. Now, let's look at this case. The same example, same 4 variables, X, W, Z, Y. The question again, okay, the same question. What's a capital sigma? It is a covariance matrix of these 4 observed variables. In this case, we have 4 observed variables, W, X, Z, and Y. And suppose this part is given, because this is a covariance matrix between these independent variables. All of these are given. But now you need to figure out these 4 elements, 4 question marks, okay? So let's start from covariance between X and Y. Okay, so we can just try to do it together. Okay, we trying to get covariance matrix of X, W, Z, Y. Okay. So suppose we have X, W, Z, Y. Here we have X, W, Z, Y. You need to figure out this part, right? The covariance between X and Y, covariance between W and Y, covariance between Z and Y, variance of Y. So that's it, these 4 components. So covariance between X and Y, covariance between X and Y. X, the top part, okay, Y. Covariance between X and Y. Let's look at the one component. Okay, the first component, if we start from Y, goes back to X. That's one path, but you have to consider the variance of X. That's one component, right? So start from Y, goes back to X. We have beta X, and then times variance of x, sigma, which is sigma x squared. That's one component. That's possible. That's possible path. Okay. Is there any other path?
There's several.
From, yeah, you're right. From y to, starting from y, stop at x. Is there any component? We can go to w first and then stop at x. In that case, we use this path. Okay, we use beta w. And then we goes to w, but you have to go back to x. So there's a double-headed arrow connected w and the x. So you have to use this covariance stopped at x. So that is covariance between w, x.
You know y, z, and then up to x for a double-headed arrow as well.
Yeah, that's one component. And you can also use this path.
Mhm.
So we have beta
Beta z,
z times covariance between
xz.
z and x. Yeah, it's the same. Z, the covariance between z and x, covariance between x is the same thing. Okay. Any other component? Let's look at that path. Maybe it's better. Any other component?
Beta W, beta Z
Beta w
times beta Z.
times beta z, beta w.
Yeah, I was thinking of trying to
Become beta
incorporate
Z.
their covariance. somehow as well. Maybe covariance of W and Z, but I guess.
But we have to stop at x. Yeah.
From Z to W to X.
From z to w to x, but you have to start from y.
Yeah,
Oh, you
Y to
mean
Z
this
to
one?
W.
yeah. Y to Z to W to X.
But you use it
That's
twice,
two-
the double
two
headed
double
arrow twice. Yeah, if we use this, okay, from w to z, go to w, then we have covariance between these two. Go to x, you have another covariance, double headed arrow. That's not allowed.
Are we able to go through y twice or no?
No, because this is a covariance between x and y.
Okay.
Yeah.
I was thinking of going over to the error and back up to x, but you use y
Yeah.
twice.
That's it, I think. Let's go to check the correct answer in the first by using the first method. This is a component by using, I'm sorry, this is really hard to see. This is a component. Let me just copy this matrix again, and then we can check it. So, let me- Yeah, let me copy this one. Okay, so,
I have a question.
yeah,
Oh, sorry. This is how my brain is processing it for the path from beta Z. to
path
Y.
from beta Z.
Mhm.
So from here to stop here and it goes to X.
I was just about to say, I was just about to ask, it incorporates all three covariances.
Yeah, covariance between X and Z.
Okay.
That's one component from X to Z, the
Mhm.
beta Z, and the covariance between X and Z.
Okay.
Yeah. Actually, if we check the final correct answer, that's it. So we have the component starting from beta X, variance of X, that's one component,
Mhm.
and it goes to W, and the
Mhm.
covariance between X and W, second component, and it goes to Z, and the covariance between X and Z, that's it. We just formed the
all three correct components. That's good. Again, by using this rule, we don't need to do any algebra calculation. We don't need to replace the components of the model and then do the extension. That's not the, yeah. So
This was a lot easier than the algebra for.
okay, you think it's easier?
No,
Because this example is easier. If you have very complicated path, you will got lost. Okay, how many components? How many paths? I forgot. It's not easy actually. Okay, so let's look at the where is it?
well, my
yeah, the
brain
other-
understood this easier than the algebra did.
Because this example is easy. Okay, so we just figure out this part. Done. Similarly, we're gonna consider the covariance between W and Y. Okay, covariance between W and Y. Same thing. Okay, W and Y. Covariance between W and Y. So you can. This is symmetric. So actually, it's symmetric.
Yeah.
You go to this way.
And then back.
Yeah.
Go
You don't
down,
need to go back. You have to stop here because it's W. Go to this way
and then go up. Yep.
and then go that way.
Yep.
Three components. So it's quite easy for us to write down these three components. Beta
W.
W times variance of W. That's one component.
Plus-
Start from here, stop here, the variance part. And you can also use
Beta Z.
beta Z times the
Times.
covariance between Z and the W. Now it's a covariance between Z and the W because you have to stop at the W
Mhm.
and then go to X. Okay, beta X and stop at W. So covariance X and the W. That's it. We have three components. So we have one more. Okay, for covariance. Z and Y, okay, Z and Y, same thing. Z and Y, so you start from Y,
Mhm.
goes to Z, variance of Z, stop here, one component. You start from Y,
Go to
go
W.
to W,
Go down.
yeah, go down, Z, yeah, you have to use this covariance matrix and stop here. You start from
Y to X.
Y, go to X, and then stop at Z. So we have three components again, beta Z, and the variance of Z, and the beta X, suppose it's X, so covariance between X and the Z, and the beta W, covariance between W and Z. Okay, done, three components. And that's obviously our correct answers for these three question marks, or these three covariance part. Done. All of these are here. Now, let's look at the variance of Y. Variance of Y. Okay, again, let's just look at the path diagram. Variance of Y. It's not easy actually.
This one's gonna have the extra component you using the error, correct? So it'll have
Yeah,
four.
you're right.
components.
You are right. Okay, you have said 4. That's
7.
4.
7? Oh, okay.
Okay,
I just
anyway,
went,
let's start from with, okay. Covariance between Y and Y. Oh, variance of, this is a variance of Y, start from Y. There are so many possible ways. Starting from Y goes back to Y. Okay, let's just look at one possible. We can go to X and go back to Y. That's very simple case. Okay, so we start from Y, go to X. So we have beta X and the variance of X,
and then beta-
You have to go back to Y.
beta
Go
X.
back to Y, beta X. That's one component.
The other one's using Y to 1. Go to
Okay, you
E
said go, okay, that's
E.
good. Okay, so you said 1
times variance of
times
E
variance of E
times 1.
times 1. Go back to 1. Good. And you can use W. Okay, suppose we use starting from Y
Beta
goes to
W.
W. So beta W, variance
Variance
of W,
W. Beta
and then
W.
go back to again. W. Then you can use this path again. Yeah, this component. So starting from Y, go to Z,
Oh, you're right,
variance
7.
of Z,
You're right, 7.
and go back to Y. Okay, beta Z again. Is that all?
No,
No. There any component, any other component?
No.
How?
You can go to Y to W, up to X and back down.
Back down to Z.
Either one.
You
Either
are
one.
right.
You can go Y to W, down to Z, up to Y, Y to W, up to X and back to Y. You
Exactly.
know, so Y to Z, up to X and back down.
You're right.
So
You can just follow this way or follow this way
Uh-huh.
or this way
uh-huh.
or even reverse. Okay.
Oh shit, I didn't think about
Go
reverse.
this way,
So there's
and this way.
14.
Yeah, there are
Wow.
so many possible ways to get back to Y. So let's just make it very clear, okay? Because it's now it's quite confusing now.
I didn't think about
So,
the reverse.
We have already used a variance part. Now look at the covariance, double head error between two variables. You can start from Y to X first, okay? Then it is the beta X. Now we stopped at X. We have this way to go back. We also have this way to go back. So there are two possibles. Actually, there are two possible ways. So you can use this path. In this case, we have to times the covariance between X and W, okay? Covariance between X and the W. And then times beta W. This is one path, okay? Beta X times covariance between X and W. Use a beta W. I'm sorry, this is a beta X, this one. This is one component. Actually, we can also use this way. Okay, starting from beta X goes to this path, go to Z, and then stop at Y. So in this case, we're gonna use covariance between X and the Z, and use a beta Z. Yeah, use a covariance part. And then we can also use this path. This goes to beta W. Starting from Y, go to W, and you can go to this path. Okay, go to X, stop at Y, or use this way. Go to Z, stop at Y. So here we have components, two components. So beta W, covariance between WX and the beta X. And if you use Z, then you have covariance between WZ and the beta Z. And also you have another path, possible path, okay, starting from Y to Z, okay, then beta Z here. Stop here, and then you have this way to go back, you have another way to go back, okay? So you have covariance between, suppose we use this path, then ZW and beta W. And Z covariance between X and Z, and the beta X. Okay, so we have this component, all of these components. In total, how many components? Actually, here we have 2. Okay. So here we have 6. We have 10 components. Of course, some of them, finally, we're gonna reorganize these components by combining similar terms. We have different similar terms. For example, beta X, beta W. Here we have beta W, beta X. So these two are the same, okay? Beta X, beta W, covariance between X, W, okay, beta X, beta W. So you can combine these two by timing 2 times, okay, these two terms. And also beta X, beta Z, here we have beta Z, beta X. These two are the same. So we combine these two terms. Also W and Z, W and Z. So we combine similar terms. And if you look at the path, actually, so if you start from Y to Z, goes to X to stop at Y, this component is different than this component. There are two components. Although the path is similar, but the order is different. We use this order or use this will be considered as two different components. That's why we have 2 times that component, okay? So you're gonna combine similar terms together. We have 3, this variance part plus the residual variance part. And here, all of these are 2 times the covariance part, okay? So finally, we have the variance of X like this, okay? So these 3 components are variance part. This is the residual variance part. And we have 2 times this covariance part. We have covariance part. In total, we have 10 components. Okay, of course, after we combine some components, now we have a shorter form. Okay, so that's a variance of Y.
I can see how that get complicated quick.
Exactly. It's only a multiple regression. And there's only 3 independent variables. If you have 10 independent variables, it's gonna be very, very messy. But anyway, this is a very, how can I say that? It's very helpful for us to understanding how to get the covariance matrix, okay? Although, yeah, it's not very practical when the model is complicated. Any question? Yeah, question?
Is there a way to know how many components?
It's really hard. Yeah, it's not easy. You can, as you can tell from this example. Yeah.
So there's like no right or wrong, like number of pathways, or do you need to get all of them?
You have to figure out, yeah, the all possible components.
Okay.
It's very easy for you to miss one. Then the final answer will be wrong.
Okay.
So for the homework 2, you're gonna use a choosing method to redo your mediation model. You're gonna compare your final answer with your answer from the first method to see if there's something wrong. If you miss one term, that means, okay, maybe I missed one path, or maybe the first homework 1 has some mistakes. You can just do the comparison by using these 2 methods. Yeah. The final answer should be exactly the same, although you have different methods. Yeah. Yeah.
If we get points off on our first homework, can we redo it using this and show you?
Okay. Yeah. Okay.
Does
That's
that make sense?
okay. Yeah. So if you
Because I've already seen some mistakes I've made on homework 1.
okay. So if you figure out that you have some mistakes in homework 1, you can just resubmit it to me.
Okay.
Before I give you back the homework 2, graded homework 1 and homework 2, I can just think about its resubmission is just like a, yeah, you can have a second chance to do that. Okay, so that's a second example. Okay, homework 2, that's
Yeah.
your model. That's your model again, mediation model. By just looking at the path diagram, you're gonna think about the covariance matrix. So in this case, we only have 3 variables. So 3 variables is 3 by 3. Okay, in total 9 components, but some of them are known. So some of them are symmetric. So let me explain the homework 2 for you. So you have 3 variables. So you're gonna calculate the covariance matrix between W, X, and Y. So that means, okay, suppose this is W, X, and Y here, W, X, and Y here. this part is given. Suppose this part is given. Sigma W square is given. Then you need to know this part, this part, this part, this part. 5 question mark. It's again the same questions as in the homework 1. So that means what is the covariance between W and X? Okay, W is here, X is here. What is the covariance between W and X? By using the tracing method. Show me the correct order. Which one is the first step? Which one is the second step? Which one is the third step? Okay. And then this is a covariance between W and Y. Okay. Covariance between W and Y. Again, show me the correct path. Okay. And variance of X. Variance of X. Here, X is here. Variance of X. By looking this path diagram. Covariance between X and Y. Okay. Covariance between X and Y. X here, Y here. Covariance between these 2 variables. And the variance of Y. Variance of Y. Okay, 5 components. You can also show me the paths. For example, you have these paths. Okay, you can just show me starting from Y and goes to C, goes to, by using the path of C, start at W and the variance of, this is one component of Y. Okay, this is just one component of variance of Y. So you can just show me the path. Show me the path, or just write the coefficients and the variance of covariance part. Clear? Is that clear? This is your homework 2. Okay. Yeah, question. Yeah, question.
So in my mind, I process things. So for example, for W, would the answer be hypothetically, do we have to use A or W?
A or W?
Yes.
A is a coefficient between from
Yes.
W to X.
Right. So I was trying to practice doing it in my head. So would the answer be W sigma W squared times W?
Which component are you going to take? Is the covariance between X and the W? Which or the variance of X? Which component?
The variance of W.
We already know.
The
That's
variance of W is given. This part is given. You don't need to. Yeah, this is given. Yeah.
That's the only one that's.
Yeah. Based on
So
that, you can just
figure out the
derive.
others.
Yeah, many other components.
I have a question. How did you know when to stop? Like when you say,
That's a good question.
like, I remember you guys, you select covariance from X and Y, you start with Y, you need to end up at X. So then when we have covariance of W and X, are we start at X and we
Yes.
want to end at W?
Yes.
Okay.
Yeah. Always start from the dependent variable. Because here, W and X, actually W causes X. There's a relationship between these 2 variables.
All right.
W causes X. W is an independent variable. X is a dependent variable. Always start from the dependent variable. And then stop at the other variable. Yeah. Any other questions? Is that clear for homework 2?
And
Okay.
that's due next Monday or next Tuesday.
Yes, next Tuesday. Yeah. Yeah.
And you have
Question?
5 homeworks, right? Or 4.
It depends. Maybe 6, maybe.
Oh,
I
you're
said,
killing me,
I
Smalls.
said that this course might challenge you, okay? That's not an easy course, okay? So, is that clear?
Yes, ma'am.
Okay,
Oh, wait, I have one more question.
Yeah.
Because on the part of, wait, it says part of homework 2, is there, a
yeah,
place
you're right.
where-
There's another part
There's
of
another
homework
one.
too,
Okay.
by using the third method.
Oh, well, no, because I'm saying for like, what you want us to figure out the covariance, do you have that like listed in like the homework 1, you had us answer like you wanted this one, this one, this one.
Oh, yeah, that's it. You have to figure out these 5 components.
Of those 5.
But by combining these 5 components, you have to provide these. You have to provide these covariance matrix. Yeah. The final goal is trying to figure out the covariance matrix of this model. This model have three observed variables, W, X, and Y. So the covariance matrix is just like this. But this part is known. All of these are unknown. So you have to figure out by using this method.
So
Yeah.
what she's asking is on a homework one, you had a sheet with this diagram and it had a list of each one of the items with a point value.
Okay,
of
I have
each
the point value.
question.
Yeah, let me think about that. How about that? Because based on my original plan, you have two parts for homework 2. One part is for using the choosing method. The other part is by using the matrix algebra. How about dividing into 2 homework? So this is homework 2. Homework 3 will be the third method. All right.
Yeah, sure. Piecemeal, eat an elephant one bite at a
Okay.
time.
Okay, then that's your homework 2. Okay, that's your homework 2. It's due next.
Did I understand your question, right? Is that what you asked?
Yes, yeah,
Okay.
because I just wanted to know which elements we're supposed to look
Yeah,
for.
the paper.
Yeah, that one part, like, yeah.
Okay, I will show you the. Okay, so we can just stop here, maybe have a break. Any question? Any question for the second method? Actually, I think in the last page of this lecture, I gave you the grading policy. Yeah, grading. Again, based on the original plans, 5 points for the first part. So here, this is your homework 2. Okay, so by choosing method, figure out each component of the covariance matrix, and second part by using the RAND calculation to calculate this part. So now if we calculate, yeah, we can separate this into 2 parts. Then 10 points for the first part. 10 points. So we have 5 components. So I'm gonna change the policy here. So this is really easy. This will be 1 point. Okay, this is 2 points. This is 2 points. This is 2 points. This is will be 3 points. So 10 points. Okay, so this part, if you get this part correctly, 1 point, and if you get these 3 components and 2 points for each component, and variance of y 3 points. Okay, so in total 10 points. 10 points. And then again, you have to give me the order. No full stores if there's no order. If you just copy the result from the homework 1 and show me the final answer, no points, because I don't know how did you get that final answer. Okay, just show me the test. Okay, clear? Good. Then let's have a break, and then we can continue the second part in 15 minutes.
Sounds like we need to get a group chat going.
Okay, let's continue the third method. We have already finished the 2 methods, and let's look at the third one. It's called the RAND method. Actually, it's short for reticular action model matrix. By using this method, we're gonna figure out some matrix, and then we do matrix algebra, and finally we got the final covariance matrix gets a sigma, capital sigma. Actually, all of this computer software, okay, you're gonna use M+ or R or MS or any software. They use this method because this is very easy for computer to do the calculation. Okay. And in order to use this method, you have to figure out the 3 matrices. Okay, so F, A, and S. That's it. First step, you need to figure out these 3 matrices, and then by combining these 3 matrices by using a formula, I will give you the formula if they don't. And the next part, I just do the calculation. That's it. It's really easy. So let's look at these 3 matrix. Okay, so F is a rectangular matrix to distinguish observed and latent variables. I will tell you what's the observed variable in the model and what are latent variables in the model. Okay, and A is a short for asymmetric A is the first letter of the asymmetric. It stores all single-headed arrows in this matrix. Okay, and S is short for symmetric. Is the first letter for symmetric. Okay, this matrix gonna store all double-headed arrows in that model. So all single-headed arrows, paths are stored in the matrix A. All double-headed arrows are stored in the matrix S. And F is rectangular matrix to distinguish the observed variables and the midterm variables. Okay, so this is a general introduction of three matrix. Again, let's look at the simple regression case. We have X causes Y, and of course we have the residual part. We have the E part. Now the question is that what are these three matrices? Okay. So what is F, what is A, what is S?
So the double-headed arrow is A, correct?
Yeah, there's some rules. There's some rules to generate these three models. Oh, not models, three matrices. Yeah. Double-headed arrows are here. Single-headed arrows are here. This just tells us observed and other. So let's look at it. First, let's look at the variables. Okay, in this case, actually, we have two observed variables, just X and Y. These are two observed variables, but here we also have the error part. This part is not observed, direct observed. Actually, we use a circle to show it as the error part. By combining the error part, actually, we have another set of variables, all variables. In addition to observe the variables X and Y, we also have the E. E is a latent, it's a circle, but included in this model. So we have observed variables X and Y, we have all variables X, Y, and E. Okay, two sets of variables. Now, in order to create the F matrix, we have some rules. First, the F is called a field. Okay, it's the first letter of the field. Field matrix, it's rectangular matrix. These are rows, okay? Observe the variables on rows and all variables on the columns. So in order to figure out the F, observe the variables. Observe the variables. In our simple case, what are observed variables?
X and Y.
X and Y. X and Y. And rows, okay, rows, we have X and Y. And
Columns, X, Y,
all variables on columns, okay, we have X and Y and E. And we have X, Y. So that is a rectangular matrix. But what elements inside this matrix? What are these elements? Only 1 and 0 are allowed. So inside of this matrix, either 1 or 0. So which element will be 1? Which element will be 0? With 1 denoted an observed variable.
So anything with E inside it would be 0. And
Exactly.
anything with X and Y is a 1.
Yeah. So
With a
here,
crosshairs.
this is 1. This is
Yep.
observed variable. This is 1. This is
Yep.
observed variable. All of these are 0, 0. Okay, this is F matrix. Okay, F matrix done. Yeah, that's it. That is our F done.
So the reason X, Y is 0 is because it includes E, correct? Why did you do X, Y as 0? Can you explain that to me?
So that means X and X, yes, it is observed variable. And X, Y, no, these are different letters. Okay, and the Y and Y, it is observed variable. And all of these, okay, X and E and the Y and E, no, they are no relationship. Yeah, I just showed the 0.
Oh,
Yeah,
okay.
yeah.
I'm sorry.
yeah. So these.
So I thought since X and Y were both observed, the corresponding core would be 1 as well, but
No.
okay,
Yeah, okay,
thank you.
that's F. And then let's look at A. It's asymmetric matrix. It's shorter for asymmetric. And in this case, we're gonna use all variables instead of observed variables. So that means we have X, Y, E here. We have X, Y, E here. So we have 3 by 3, 9 elements needed to be filled. Okay, we needed to figure out the 9 positions. And I'm gonna save all single-headed arrows here in this matrix. And what are elements inside the matrix? These are coefficient of the single-headed arrow, such as beta or beta z, beta x, beta something like that, or single-headed coefficient. Okay. How are we going to read this matrix? We're gonna read from columns to rows. So starting this path diagram. Okay, we have x here, we have y here, we have e here. This is a beta. And of course it has okay. Now let me ask you, from x to x, is there any single-headed arrow from x to x? No. If there's no single-headed arrow, 0, just put a 0. From y to x, is there any single-headed arrow from y to x?
Yes.
From y to x,
No.
from y to x,
Oh,
no, 0. Okay, 0. From e to x, is there any single-headed arrow? From e to x,
No.
no. From x to from x to y, is there any single-headed arrow?
Yes.
Yes. What is the coefficient?
1.
Beta. Beta should be put here. This is beta. From x to y. From y to y, is there any single arrow? No, 0. From e to y, is there any single head? The single-headed arrow.
Yes.
What is the coefficient? Yes, just put 1 here. That's it. From x to e, is there any single-headed? No. Okay. From y to e, no. From e to e, no. That's it. This is our A matrix. Okay, this is our A matrix. 3 by 3.
So for this, when you say the single head arrow, you must go the direction of the
Exactly.
arrow. It's not
From-
backwards like before.
That's why I asked you from x to y.
Gotcha.
Here's a single-headed arrow. From y to x, no. From y to x, no.
I was still going backwards from the other
No.
rule.
If you have this way, then you can say that there's a
Sure.
single-headed. Yeah.
Thank you.
Okay, that's it. That's our A. Clear? Okay. We have already talked about that. Let me write down all of this matrix somewhere because we're gonna use this.
Space.
Yeah, so we're gonna F is 1, 1. No, 1, 0, 0, 0, 0. And A is 0, 0, 0, beta 0, 1. Now let's look at S. Okay. It's for double-headed arrows. And again, it's for all variables on rows and columns. So we have X here, we have Y here, we have E here, we have X here, Y here, E here. Now let me ask you, from X to X, is there any single-headed arrow? So let me just write the coefficient. Yeah, so the path diagram again. From X to X, is there any double-headed arrow?
Yes.
What is the variance? What is that variance?
Sigma S squared.
Yes, sigma x squared. That's it. From X and Y, okay, based on X and Y, is there any double-headed arrow? X and Y? No.
Error, error.
Between X and E? No. Between Y and X?
No.
No. Between Y and Y? No. Between Y and E?
No.
No. Between X and E?
No.
No. Between E and Y?
No.
Between E and E?
Yes.
What is the variance?
Sigma E squared.
Sigma E squared. That's it, done. Okay, done. Double-headed arrow, 2, okay? So this is our S. So we have already obtained the 3 matrix by using the definition or by using these rules to get them.
I
Okay.
have a question.
Yeah.
So in matrix A, you had a tip that says like read from columns to rows. Is
Yes,
there a
you're right.
specific One for matrix F and matrix S.
For S, it's double-headed. I don't know if it's from a column to row. It doesn't matter
Okay.
because it's double-headed arrow.
Okay. So
And for A, you are right, from column to row. And for field matrix, it doesn't care. So it just shows the observed variable. One means observed variables. Yeah. Okay, so we have already got these 3 matrices. Now, let me tell you the formula to combine all of these matrices together. That's it. This is the formula. Just follow this formula to calculate that. Finally, you will have capital sigma. So let me explain this part, okay? The first matrix F times, what is that? Inverse of identity matrix minus the A matrix. So we got the A matrix. Identity matrix is very special matrix, identity matrix 3 by 3, okay? The difference, got the difference between these 2 matrices, and then calculate the inverse. And then times the symmetric matrix S, times S here. And then times the transpose of the inverse of the identity matrix and the A. Okay.
Not confuse me at all.
And then 10 times the transpose of the F matrix. But why? If you want to know, okay, this is very useful, but if you want to dig deeper, why do we have this matrix? Actually, starting from, if you have all V variables, kind of like if you have this model equation, so we have the V matrix vector, we have single-headed arrow times the V, and we have the residual part, okay? So if you calculate the, assume the variance part, this is a variance part, assume the variance of the U is S. And then we can just do the algebra, okay? So we can use identity matrix minus A, and then the V's here, and use the inverse of the part. So we have the inverse of this identity matrix here minus A and times U. And then based on that, you can calculate the covariance of the V, which is sigma. So we have, by following the covariance rules, again, by following the covariance rules, you have this part, and the covariance of U, the residual part, is double-headed arrow, okay, S. And also, by following the rules, you have the transpose of the inverse of that, this matrix. And if you have filtered, okay, to tell us the variables and observe the variables and all variables, this part is for all variables. If you put the filter matrix, then you're gonna obtain the covariance matrix for the observed variables. Okay, so we have F times this part, S here, this part, and the transpose of F. So all of this derivation actually based on the covariance matrix calculation rules. Okay. So that's why we have this formula. That's why we have this formula. So next, we're gonna do the exercise. I just repeat this formula again. We have all of this matrix ready, okay? Just do the calculation, matrix algebra calculation, okay? Okay, so we start from the F. What is F? F is there. Okay, so we have 1, 0, 0, 0, 1, 0. This is our F. And another matrix, which one is identity matrix here, one identity matrix here, because we have 3 by 3 dimension. This is identity matrix minus A. What is A? A is here. Okay, we just obtained the A. Then you're gonna calculate the inverse of this difference. And then times S. S is here. Okay, S is here. And transpose of this part. Okay, we're gonna repeat it again. So there's identity matrix here, identity matrix here, minus the A here. And the inverse and the transpose. Then up we got the inverse and the transpose. And then times the transpose of the F. Okay, F is here. The transpose is that's it. So the next part is just do the matrix algebra, okay? So first step, you're gonna figure out the difference between these two, okay? So identity matrix, the matrix here, so it's 1, 1, 1 here, 0, 0. Minus W minus 1, 0, 0 here. And the inverse. Okay, so it's not easy to get the inverse of a 3 by 3 matrix, but I will tell you the answer here, okay? This matrix, the inverse of this one, the inverse of this one. And then times the S matrix here, this is the S matrix. And then times the inverse transpose, okay? So this is the inverse, the transpose of this one, the transpose, okay? And we have F here, okay, we have F here. So F times this matrix, actually, this is inverse, and the times S here times the transpose of the inverse. Let me show it's correct. Yeah. And times the transpose of the F, it's here. Okay, so we have one matrix here, second matrix here, we have S matrix here, and we have this part, we have this part. Just do the matrix multiplication.
This
I will
is
give
where-
you 10 minutes. Do the calculation. I will give you that. This matrix times this matrix times this matrix times this one times this one. 10 minutes. So you can just try to do it by yourself. And after 10 minutes, I will show you the details. I will do the
By hand
demonstration.
or using software?
Huh?
By hand.
The hand, this is easy, okay?
For the years since I did pictures.
God, I don't remember.
Oh, time is up, okay? 10 minutes. Have you got the final result? Anyone? Okay. Okay, good. So Madam said that she has already finished it. Do you want to come here to show your calculation here? Sure. Okay, thank you. You need more space. Let me give you more space. So this part that we have already done this part. So we also can, yeah, so.
Yeah, I can rewrite.
Yeah, we can remove this part. Yeah. Yeah. Okay, good. Yes, okay, yeah, that's it. Yeah. Yeah, this is
That's
S,
next.
yeah, yeah. Okay, good, yeah. So Madeline gonna show us how she finished the calculation of the discoverer.
All right, so hope you all can hear me. So this is I just start out by making sure my dimensions are right. So we have a 2 by 3 times a 3 by 3, so that works. And we have a 3 by 3 times a 3 by 3, so that works. So for this first one, because it's 3 by 3, we're going to end up with a 2 by 3. And so to get the first value, we're gonna multiply the elements of the first row here by the first column here and add them. So we get 1 times 1 is 1, plus 0 times beta is 0, plus 0 times 0 is 0. So we get 1. And then for the second column, we get 0, 0, 0. And then here we get 0, 0, 0. Now we do for the bottom row, we do the bottom row of the first matrix times the elements of the columns of the second matrix and add them together. So 1 times 1 is 0, or 1 times 0 is 0. Beta times 1 is beta. 0 times 0. So add all that up and we get beta. Now we have multiply that, we get 0, 1, 0. So we get 1 because we had 0 plus 1 plus 0. Now we get 0 plus 1 plus 0. So we get 1. Does everyone follow? So same thing over here, but I'm going to write it. Okay, so 3 by 3 matrix times a 3 by 3 matrix will result in a 3 by 3 matrix. And so we do the same thing, we just multiply the rows and columns. So for the first element, we're going to get this variance plus 0 plus 0. So that just gives us the variance. Then we get beta times the variance plus 0 plus 0. And then we get 0 plus 0 plus 0. Now for the second row, we get 0 plus 0 plus 0. Actually, they're all going to be 0 plus 0, 0, 0, 0, 0, 0. And then for the last row, we have 0 plus 0 plus 0. 0 plus 0 plus the variance of the error. And then we get 0, 0. Wait, I messed that up.
You messed up on that.
This is-
The beta and variance.
0, 0, 0, 0, 0,
Oh, I see.
error, and then 0, 0, error again. Yeah, is that right?
Yes.
Okay. Yeah, it seemed wrong. But. And then we couldn't do anything with that just yet, so I'm just gonna rewrite it. Does everyone agree so far? Okay. So now we have 2. Right, we got 2 by 3, 3 by 3. So 2 by 3, 3 by 3 is like that one. We'll get a 3 by 3. It's the same thing. I don't know if y'all can even see what I'm doing, but we get the variance of the x term plus 0 plus 0. So we just have this variance again. And then we get this beta times the variance plus 0 plus 0. And then we get 0 plus 0 plus 0. And then beta times the variance here plus 0 plus 0. And then beta times the variance plus 0 plus this error term, or the variance of the error. Okay, so I ended up with beta squared times the variance plus the variance of the error term. Right, double check that one. 0. Yep. And then 0, 0, and then the error variance. And all of that times this last guy. Still agree? Okay. And now we have a 2 by 3 and a 3 by 2. So we're going to end up with a 2 by 2. And so we get the variance plus 0 plus 0. And then we get 0 plus beta times the variance plus 0. And then beta times the variance plus 0 plus 0. And then 0 plus this long one times 0 or plus 0. So that's. So that should be,
Excellent.
yeah, that one.
Yeah, does that form look familiar to you? This form looks familiar.
From your notes.
It's exactly the same as we did before. Okay, the variance of x in this term. This is a covariance between x and y, beta times sigma x squared. This is a beta squared times sigma squared plus sigma e squared. That is the variance of y. Exactly the same matrix we obtained by using the first method and the second method. Now we use a third method. We finally get the exactly same. This is our sigma. This is our capital sigma. Capital sigma. Yeah, variance of x, covariance between x, y, variance of x. Good, thank you, Madman. Yeah, excellent. Any question for her calculation? For your homework, similarly, I will give you a very simple model. And you need to figure out what is the F, what is the S, what is A, and by using the formula, do the matrix calculation, okay? Question? Good, okay. Okay, yeah, thank you, Madeline. Thank you again. And I believe some other students may also obtain the result. Yeah, next time. So yeah, if you like, you can just come here and show your exercise to us. Okay. Good. Okay, that's for simple linear regression. We just obtained the matrix as we did in the previous lecture. Multiple regression. Oh, I'm sorry, I forgot to open the projector. Now, multiple regression. Yeah, that's we obtained from method 1 and method 2, okay? Again, in order to get FAS, we have to summarize the model by using the observed variables. We have the x, w, z, y here, 4 variables in this case. And then we have all variables. In addition to these 4, we have the error part. Okay, so we have error part. So just like the F matrix, you have F, just like the simple linear regression, I'm sorry. You have F, which is a filter matrix, and that is our F, okay? So we have observed variables on rows, all variables on columns, and 1 and 0 are inside of this matrix. So X is observed variable, W is observed variable, Z is observed variable, Y is observed variable, but these are all 0, 0, 0 because E is not observed variable. Okay, that's our F. A, same thing for asymmetric for single head arrow. So we have images like this. Okay, actually, if you have the previous pair diagram, you can just figure out. This is our. We can just write it here. Okay. So let me remove this. Okay, so we can just use this path diagram here and figure out the images. A, so we have X, W, Z. Okay, we have X, W, Z, Y, Z, X, W, B. So let me ask you, from X to X, is there any single-headed arrow from X to X? No.
No.
From W to X? No. From Z to X?
No.
No. From Y to X? From Y to X?
No.
No. From E to X? No.
No.
Okay, good. From X to W? No. From W to W? No. From Z to W? No. Y to W? No. E to W? No. From X to Z? No. W to Z? No. Z to Z? No. Y to Z? No. E to Z? No. Now, from X to Y, what is the coefficient?
Yes.
From W to Y, what is the coefficient?
BW.
Yes. From Z to X, what is the coefficient? Yes. From Y to Y, single-headed arrow. From E to Y, what is the coefficient? Exactly, 1. From W to E, I'm sorry, from X to E,
No.
no. W to E,
No.
no. What, Z to E, no. Y to E, no, no. Okay, so all of these are no, no, no. This is our A matrix, okay? This is our matrix for multiple regression. And how about S? Again, it is X, W, Z, Z. So from X to X, is there any double-headed arrow? From X to X, yes. Yes, it's variance of X. From between W and X, is any double-headed arrow?
Yes.
What is the covariance?
Variance XW.
Covariance XW, yes. Between Z and X,
Yes.
yes. Okay, Z and X. Between Y and X, double-headed arrow? No. Between E and X?
No.
No. Between X and W? Yes, okay. X, sigma XW. W and W? Yes, okay. Z and W?
Yes.
I'm sorry, W and Y?
Yes.
No.
Yes or no? W between W and Y, double-headed arrow?
Oh, no.
No.
Sorry.
E and W?
No.
No. X and Z? Yes, and X and Z. W and Z? Yes. W and Z. Z and Z? Yes. Z and Y? No. Z and E? No. Between X and Y, double-headed arrow. Between X and Y?
No.
No. W and Y? No. Z and Y? No. Z and Y and Y? No. E and Y? No. And W and I'm sorry, X and W?
No.
No. W and E? No. Z and E? No. Y and E? No. From E to E,
Yes.
double-headed arrow.
Yes.
What is the element? What is the value?
Sigma E squared.
Sigma E squared, exactly. This is our S, okay, 5 by 5. 5 by 5. Same thing here, okay, it's 5 by 5. That's it. This is our double-headed arrow here. All of these are variance and covariance between independent variables. This is among the for the residual part. And here we have all of these coefficients, okay, single-headed arrows. That's it. So we have, yeah, we just showed the F matrix here, okay, and A matrix here, yeah, and the S matrix here. Yes. And same thing. Do the calculation. So you have 4 by 5 matrix here. And here it's 5 by 5, 5 by 5, 5 by 5, 5 by 4. A lot of like calculation. But this time it's not easy for us because you're gonna calculate the inverse of 5 by 5. You're gonna use some computer software to get the inverse first and do that. So we are not going to do the hand calculation, okay? So in this case, or in the many other cases, actually we needed to use a computer software, okay? So simple one, the simple case can be done by hand. For complex model, for example, multiple regression, we can do it by computer software. We just use a simple linear regression and a multiple linear regression as our examples, 2 examples. But actually, this method works for all SEM models. Mediation, moderation, or mimic model, or other 4 SEM model. You can figure out the F matrix, the A matrix, the S matrix, and by using the formula, all the SEM models can be obtained by using this method. Okay. Of course, you're gonna use a matrix sometimes, a computer software sometimes to figure out the inverse of the matrix. Okay, so we are not going to do this, finish this by hand calculation, but I just show you the logic, okay, this method. Okay. And let's have, yeah, this is another complex multivariate regression. So we have W here, we have Z here, and the W gonna cause X, X gonna cause Y, and also W gonna cause Y, and Z gonna cause Y. And Y also we have the measurement error, the residual part here. So based on this, it's kind of like a multiple regression, but here, this is the mediation. Okay, this is a combination of the mediation and the multiple regression. So if you have time, if you are interested in this part, you can just figure out the F matrix, A matrix, S matrix, and do the exercise. This is with your exercise, okay, just for fun. Okay, so this is another example. Let's look at another version. It's called a simplified RAM notation. In the previous case, we had all of these 4 path diagrams here, okay? But we do have a simplified version. The simplified RAM is implemented in most of the SEM software. Yeah, as I mentioned, we have the M+R, we have Immerse, we have EKS, we have some other OpenMax. We also have standards from SAS company. All of these are all software. All of this method, all of this computer software use a simplified RAM method. Okay. So in the previous example, we have the 4 path diagram here. But if we ignore the residual part, this is a measurement error part. This is also the measurement error part. If you use this way, I deleted the V and I deleted the E part, but I put a double-headed error here around X. This means this variance is a residual of X, not the variance of X itself. You have to make sure the meaning here is different. So the sigma V square is not the variance of X, is a variance of the residual of X. Same thing here, because we have to use a simplified version. So originally there's a E part and the variance of B is sigma E square. we deleted that part and put a double-headed arrow here. This means it is a variance of the residual y, not the variance of y itself. Okay, the meaning is different. But here, this is a variance of z because this is a independent variables, exogenous variables. So this is a variance of z. This is a variance of w. This is a covariance between w and z. But for the dependent variable part, okay, we use a double-headed arrow to show it is a variance of the residual of that variable. Same thing, this is a variance of the residual y instead of the variance of y. So that's a kind of like a confusing part for simplified RAM notation.
So
Yeah,
on
question.
Y, you said it was the variance of the residual, but isn't
Yeah.
it the variance of the error?
Yeah,
But the
the
error
error.
is residual.
Yeah.
Okay.
So you can also talk about.
I'm just
think
making
about
sure I got the
yeah,
terminology.
yeah. This is a error part.
Is a
Yeah.
residual. Okay.
This is a variance of the error part of y. So we ignore, we just by deleting this part, put the double-headed error here, but double-headed arrow here to show this path. Yeah, and the same thing here. We just use a double-headed arrow across this.
Right, I got the top one as the variance, but since that was the error, you called it a variance as well, and that's what had confused me, sorry.
Yeah, the error part of y. This is the error part of x.
Okay,
Here, in this case, there are two dependent variables.
sorry.
One is x, the other one is y. These two are independent variables. Okay, so these are variance, but okay, this is a variance of w. This is variance of z. This is a covariance between x and z. These are truly meaning. But here,
Right.
we use a simplified version. Okay, we use a simplified version. Okay, based on this simplified version, we can figure out the F matrix, A matrix, and S matrix. And if we use a simplified version, there's a no error part, no V part, no E part. So the observed variable and all variables are exactly the same based on this test diagram, because here we ignore the circle here. We remove the circle V here, we remove the circle E here. So in that case, the observed variable is all variables. So F is identity matrix. So in this case, the F matrix is just identity matrix. Identity matrix times any type of matrix itself. So in this case, you can ignore the F matrix. So the formula becomes very simple, just a 3 matrix in the middle part without F and the F transpose, because in this case, the F is just identity. The transpose of identity, it's just identity. Identity matrix times any type of matrix, it's the original matrix. So we only needed to figure out the S matrix, A matrix and S matrix. Okay. Okay, so yeah, so this is the example. So we can just do it together. We can just do it together. Okay. So the observed variables are wx, w, z, y. Okay, this is the observed vector, observed variable vector, 4 by 1. Okay, 4 by 1. 4 variables. So by looking at this, anyway, this is x. Okay. By looking at this path diagram, so let's figure out the A matrix. So we have X, W, Z, Y, X, W, Z, Y. Single-headed arrow from X to X. Is there any single-headed arrow?
No.
No. From W to X. From W to X.
Yes.
What is the coefficient?
beta WX.
beta WX. From Z to X,
No,
no. From Y to X,
no,
from X to W. From W to W,
no,
from Z to W,
No,
from Y to W,
no,
no,
from X to Z.
No.
From W to Z,
no,
no,
from Z to Z,
no,
from Y to Z,
no.
from X to Y, from X to Y,
from Z to Y there is.
from X to Z to Y, I'm sorry, Y to
Z to
Z.
Y.
So this X is from Y to Z.
Okay.
No. From X to Y. X to Y. What is the coefficient though?
Beta X.
From X to Y, beta X. From W to Y,
Yes.
Beta
beta
beta W. From Z to Y,
Yes.
Yes,
beta
beta
Z.
Z.
from Y to Y. No,
No.
that's it. Okay. This is our A matrix. S. So we have X to X, double-headed arrow.
Yes.
What is that variance? What is that?
Sigma B
Yeah.
squared.
X to W, between X and the W, between X and W, double-headed arrow.
No.
No. Z and X, double-headed arrow.
No,
Between X and the Y, X and the Y, double-headed arrow.
no,
No. Between X and the W, no.
No.
Between W and W, yes. That's it. From between Z and W, no. Between,
Hold on, hold
Wait,
on,
so-
hold on. Z and W, yes.
yes.
I'm sorry, yeah.
Sigma.
Z and the W, so sigma, yes, all right. WZ. Between Y and the W, Y and the W,
No,
No,
X and the Z, X and Z. Z and the W, Z and the W.
yes.
Okay, this is
Sigma WZ.
yeah. Z and the Z,
Yes.
yes.
yes,
Z and the Y,
No.
no,
X and the Y,
No.
W and the Y,
No.
Z and the Y,
no,
No.
Y and the Y.
Yes.
Yes, okay, that's it. This is our S 4x4. Okay, again, this is 4x4. Yeah. So that's S, that's. Yeah, so you can do the comparison. Yeah, that's X. Yeah, the same here. And S there. Yeah, S there. And using the formula, do the calculation. And again, it's not easy because you're gonna figure out the inverse of 4x4 matrix. You have to use a computer software. Okay, that's an exercise for another example shown here. So we have already finished the third method. I didn't do the hand calculation, okay, here. But finally, you will, yeah, after the formula, you will have the capital sigma matrix of that model. So any question for the third method? 3 matrix, FAS, that formula, that's it. Okay. Okay, so far we have already go through all these 3 methods. Method 1, just do the algebra calculation. Method 2, choosing method, following those rules. Method 3, the matrix calculation. For the same model, you can verify it. The answer will be exactly the same, although you use different method. Okay, so the final answer is the same. So that's for our summary. Yeah, so done. And that's it. That's for today's
talk and you do have homework 2. So yeah, again, original plan that you have 2 parts. This is the for choosing. I have already explained this part. Then for the third method, this is a simplified simple linear regression. Simplified because I deleted the error part. This means actually this is a variance of the error y, not the variance of y directly. This is the variance of the error of y. So by looking at this model, please, okay, please figure out what is the F matrix, what is the A matrix, what is the S matrix, and do the calculation by using the formula. Calculate the covariance matrix for X and Y. What is the sigma? Finally, what is the capital sigma, which is the covariance matrix of X and Y? That's your, do you want to combine these two? Do you want to do these 2 parts as your homework 2? Or you want to separate it as homework 2 and homework 3? Do you want to do this as your homework 2 and do this as your homework 3?
Personally, I'm indifferent. What's the class like? I don't want to speak for everyone.
Okay, Madam said keep them together. Is that good? So 1 week. 1 week to do these 2 parts. Okay, then okay, we're gonna stick on the original plan. 5 points here, 5 points here. Here we have 5 components. Okay, so you have 5 points, each component 1 point. And here, yeah, also you have 5 points. If you give me the correct A matrix, 1 point. If you give me a correct S matrix, 1 point. If you write down the formulas correctly, 1 point. If you got the final calculation correctly, 2 points, okay? So in total, 5 points for the second part and the 5 points for the first part. And if you didn't give me any detailed calculation, no point, okay? For this one, if you didn't give me the correct order, no point, okay? And you can also verify this part with homework 1 because this actually is exactly the same model. This is a different, okay? This model is different. This is simplified simple linear regression. Clear? Okay. Any question? That's it, okay? This is our class today, and see you next Tuesday. And the homework 1, okay, yeah, homework 1. If you have the paper version, just give me the script. If you, yeah, just want to submit the electronic version, send it to me tonight, okay? And there's a folders in the ELC. In ELC, there's a folders, tools, and then assignments. So there are a lot of folders.
Yeah, if you click on content though.
Content here.
Yeah, there's an assignment folder down at the bottom, and that's what I clicked on, and I'm like, it's empty.
Yeah, I think I needed to delete originally, I want to put all the homeworks in this folder. Actually, it's not necessary. Yeah.
I was just, I looked and I'm like, oh, nothing. I didn't go under tools, and I should have. I'm sorry.
You have good night. Okay.